And so now we have to decide what different circuit elements do to our phase. Okay? So we'll start with this, the most straightforward one. If we have a resistor circuit, okay, so if we look at the so we have the voltage that's our input, and then we have the voltage across our resistor. Here we have current and voltage, right? You'll see these for DC are pretty straightforward. They're both flat, okay? If we have AC, here's current and voltage. What would you say about the phase of the current and the voltage across the resistor? It's the same, right? These things are in phase. That means they start at the same point. They have the same frequency. No big deal, okay? Now, I also want you to notice for DC circuits, we have capital I current and capital V voltage, right? For AC circuits, what do you notice about the current and voltage? They're lowercase, okay? So this is the instantaneous current and the instantaneous voltage. Now, why do we have to talk about the instantaneous things?
It's changing.
It changes, right? What's the current and voltage here? Zero. What's the current and voltage here? Maximum, right? But obviously not zero. So at each point, right, if we draw a vertical line here, that corresponds to a particular time. At that instant, we have a current and a voltage, but they change over time, right? Now, you'll notice there's still some capitals. There's I naught and V naught. What do those represent?
The max.
The maximum current is I naught, okay? So the range of the currents available to you for instantaneous current are everywhere from negative I naught to positive I naught. Okay, the range of voltages available to you in AC are everywhere from negative V naught to positive V naught. Okay, so we have to start thinking about, well, what's the current and voltage at a particular time rather than what's the current and voltage all the time. And you'll find that a lot of the math, a lot of the stuff we can do with circuits, we can still do loop law the same way, but we have to be careful about whether we're talking about the maximum current or the instantaneous current. All right? So, if we look at Ohm's law, we say, well, now the instantaneous voltage across the resistor is equal to the instantaneous current across the resistor times the resistance. So this is still Ohm's law, okay? But instead of saying V equals IR, we've specified that this is for each particular time. All right? So basically, if we have a current going through a resistor, V is going to be equal to IR still, but now it's instantaneous voltage and instantaneous current. So the way we draw these things is our voltage source is not a battery anymore, okay? Now it's a circle with a squiggle in it. What does that mean? It's AC, right? Your input is a sine wave. Your voltage moves in a sinusoidal fashion, okay? Then when you take your voltage across your resistor, the voltage across the resistor changes because as your voltage from your voltage source goes up, the voltage across your resistor also goes up, okay? So if you want to figure out the current, V, the voltage, is going to be V, maximum V, cosine omega t. R is still just a constant, so you end up with V over R, which gives you your maximum I cosine omega t. Okay, so we're still using V equals IR. We have now the peak current and the instantaneous current. So this is an expression for the instantaneous current in terms of the peak current. Okay, so you have a cosine wave that oscillates between the maximum current on both ends. All right, so if you want to plot these together, here's your voltage, okay, it's a cosine. Here's your current, it's also cosine. They have the same frequency omega. And where do we get that frequency omega? Where does it come from? How do we introduce it to the circuit? Let's say your voltage source is from the wall, okay? What's omega?
It's the inverse of the frequency.
Yeah, it's the angular frequency, but like, what comes out of the wall? What frequency?
It's 120 hertz.
It's 60 hertz, right? 60 hertz times 2 pi. So omega would be 2 pi times 6, so 120 pi. So somewhere in between the two things that we said. But omega would be 120 pi radians per second. Okay, that's because it depends on your voltage source. So omega comes from your voltage source. All right?
Yeah, but
So-
where did the frequency come from?
What?
Where the frequency?
From the voltage source.
No, where the 60 hertz?
That's
That's
what comes
standard.
out of the wall. That's standard.
But how do they know that's 60 hertz?
How does who know? Like that's how the signal that they're sent. Like it's determined by people who send power out to neighborhoods, right? That's determined by the power plant. Okay. You can set it to different values, right? In different countries, sometimes you'll have a different frequency, but this is just a standard that we've decided as a country.
Alright.
You can measure it. All you need is a multimeter or an oscilloscope. No, not to, or a fork.
A fork.
Like, oh yeah,
That feels about 60
Just as a
hertz.
disclaimer, for those who may be listening or watching at some point,
Like-
do not stick a fork in there.
Yeah.
Okay, I'm not advocating that. That is a joke. Okay, so if you want to figure out your instantaneous current, you get your maximum current, right? That's your that's from V equals IR. Okay, that's your current for your peak to peak, right? And then this is your maximum current cosine omega t. Okay, and you'll notice current switches direction every half cycle because you're oscillating back and forth. All right, so how do we plot this as a phasor? Well, it's pretty straightforward. Okay, the resistor and the instantaneous. We know they always have the same phase. That means they move together. Okay, so as the voltage moves, the current's just right on top of it, and they rotate at the same speed because they both have this angle omega t. If you want to calculate the instantaneous values, you just project them along the x-axis. Okay. All right.